In this lesson, we will use the many circuits that we have learned in order to build the basic blocks for a synthesizer. Even when all the circuits we will see work fine, they have been designed to be easy to explain. They strike a good compromise between the simplicity and the performance, and they will help you understand more complex or professional circuits. We will start with a circuit called low frequency oscillator, or LFO for short. As its name says, this is an oscillator that works at low frequencies. The range can go from less than 1 Hz to a few kHz. The main applications of this type of oscillator is to generate modulation signals, for example, to slowly change a sound and adding variations. We can build an oscillator like this with 3 subcircuits: an integrator, a comparator, and a voltage divider. The circuit works as follows. Initially, the comparator outputs a positive voltage. In this case, it will be 12 volts. That voltage goes into the voltage divider and it's scaled to around 0.56 volts. That voltage is given as input to the integrator. Since it is a constant positive voltage, the integrator output will decrease because it is an inverting integrator. The value will continue decreasing until it reaches the low threshold of the comparator, which in this case is around minus 5.5 volts. At that moment, the output of the comparator suddenly changes to minus 12 volts. Now the input of the integrator is negative, therefore the output will increase. Once it reaches the high threshold, which is around 5.5 volts, the comparator changes and the process repeats. In order to control the frequency of the oscillator, we need to control the gain of the integrator. In this case, we have added a potentiometer of 1 megaohm in order to get a wide range. There are other ways of changing the gain of the oscillator, like changing the capacitor value, but it is easier to change the resistance. From this LFO, we can get 2 types of waveforms, a triangle and a square wave. One variation that we can do to this circuit is making possible to control the frequency using a voltage signal. In modular synthesizers, it is very common to control the parameters of modules using voltages. That way we can create all kinds of crazy sounds by interconnecting the modules. This can be achieved by replacing the integrator with a voltage control integrator. In a previous lesson, we learned how to do that with an operational transconductance amplifier. In the diagram, you can see the integrator using an OTA. The comparator is exactly the same. When a positive 12-volt signal is output, that goes into the resistor divider formed by resistor 5 and resistor 6. With those values, the 12 volts are reduced to around 12 millivolts. Those go into the non-inverting terminal of the OTA integrator. The external current of the OTA controls the gain, and we can adjust the range with the capacitor value. In the simulation, we can see how it behaves. It's just like the previous LFO, but the frequency changes as the control voltage increases. The LFO can be tweaked to produce oscillations in the audible range. As mentioned before, it produces triangle and square waves. We can easily derive other types of waves, for example, the pulse wave. The pulse is an asymmetric square wave as the one in the plot. The sound of this wave becomes even more interesting when we change the width of the pulse. Changing the width of the pulse is called pulse width modulation, or PWM. Here we can compare the sound of a square wave that sounds like this against the sound of a pulse wave that is being modulated. Generating a variable pulse width signal is very easy using the components that we already know. We need 2 oscillators, one that runs at low frequency, an LFO, and other at higher frequency. We take the triangle waves of both oscillators and we fed them into a comparator. In the simulation, we can see the result. The green wave is the slow LFO, the blue is the fast LFO, and the orange is the pulse width modulated. We can see that every time the fast signal is lower than the slow LFO, the comparator outputs a positive pulse. We do not need a slow LFO since we can provide a fixed voltage that is given by a potentiometer in the module, and with this small addition we can add an extra wave to the oscillator. What if we want to start playing actual music using this oscillator? That will be a little bit hard, since it will be hard to match the control voltage to a specific note. In order to simplify that, we need an oscillator that follows the standard of changing 1 octave every volt of the control signal. For example, for a control signal of 1 volt, the output frequency could be 110 Hz, which is an A2 note. With a control signal of 2 volts, the frequency has to double, so it will be 220 Hz, which is an A3 note. A signal of 3 volts has to double again the frequency and produce 404 Hz, We can improve the control of the OTA integrator by using a linear voltage to exponential current converter. In the diagram, we can see a circuit that does that job. We are not going to analyze it in detail since it relies on the behavior of transistors and we have not covered them in this course. However, this circuit works fine when I build it. It just needs a small calibration potentiometer in place of resistor R3 to adjust the node tracking. In the simulation we can see how it performs. In the top we can see the input voltage that goes from -5 to 5 volts. We can see that the control current increases exponentially to 1 mA, which is good enough to control the OTA. To use the converter, we simply take the oscillator circuit and we connect the voltage to exponential current converter into the control pin of the OTA. In this circuit, the only change I have made is to reduce the integrator capacitor to 1 nanofarad. That way, the oscillations are in the audible range. In the simulations, we can see the behavior. With a control voltage of 0 volts, the output, which is shown in blue, produces a single cycle of the wave. When increasing the control voltage to 1 volt, the output, in orange, produces 2 cycles in the same period. That means that the signal is 1 octave higher. This oscillator now follows the 1 volt per octave standard. There is another simple circuit that we can make in order to produce an extra wave in the oscillator, a sawtooth wave. To produce a sawtooth, we need to take the triangle wave and connect it to a simple inverter. This produces a signal like the one shown in the simulation. We can pass these 2 triangles to a switch. If we use as selector the square wave, we will obtain the wave shown in the plot. The sawtooth wave is built with pieces of the 2 triangles. When the square is 12 volts, we pick the regular triangle shown in blue. When the selector is -12 volts, we pick the inverted triangle shown in orange. It is important to notice that this saw wave is 1 octave higher. In practice, it is not a problem since I find that it sounds very nice in combination with the other waves. We have been talking about getting different waves, but you may wonder how do they sound. Let's compare the sounds. The triangle wave sounds like this. It has a kind of smooth sound with a little bit of bright elements. Now compare it to the square wave. This one has a lot of harmonics and it has a kind of strong sound. The next one is a pulse with a fixed width of 10%. This one sounds like a square wave but with a nasal sound. And last, the sawtooth. To me, this one has a more metallic sound and less strong than the square wave. Each wave has different harmonics and you may prefer one over the other when you are designing sounds. So far we have focused on oscillators. Now let's try to create other types of modules to complete a basic synthesizer voice. In the following diagram you can see a very basic voltage control amplifier or VCA that is built with a backtroll. If you remember the previous lesson, a backtroll can change its resistance based on a control voltage. The circuit that you see is a voltage divider. When there is no control voltage, the resistance of the backtroll will be very large. Therefore, the voltage at the resistor R1 will be low. As the control voltage increases, the resistance of the backtroll decreases. That will increase the voltage seen at R1. R1 is connected to a voltage follower in order to create a copy of the signal. This circuit can lead to interesting results, but as mentioned before, depending on the characteristics of the backtroll, it may require adjustments. Let's check a better VCA circuit. The following circuit uses the OTA circuit we learned in the previous lesson. The main difference is that we control it with a circuit that converts the voltage to linear current. We will not analyze this circuit, but if you build it, it will work fine. The main advantage of this control method is that a voltage of 0 volts produces a control current of 0 amperes. In the VCA we saw in the last session, we required a voltage of -12 volts to produce 0 amperes. We are missing an important module in analog synthesis, a voltage control filter. Probably the most versatile filter is a state variable architecture that we briefly saw in the analog filters lesson. The filter consists of 2 integrators and a subtractor. In this diagram, we can see the circuit. In this case, I have replaced the integrators by the same circuit we use for the oscillators. Both integrators are controlled with a voltage to exponential current converter. In the control section in the top, the cutoff can be defined by a potentiometer, but the circuit also accepts 2 modulation signals that can come from other modules. The subtractor circuit is easy to understand. The main change is that I have added an extra input so the filter can take two signals. In the bottom, I have added a potentiometer that will help us control the resonance or quality of the filter. If you remember, the quality of the filter defines how the frequencies around the cutoff behave. In this specific filter, changing the resonance produces the following sound. For example, with no resonance, this filter sounds like this when fed by two oscillators. Increasing the resonance to 70% sounds like this. If we increase it even further, we start getting this vowel-like sound. The only block that we need to complete a basic synthesizer is an envelope generator. Envelope generators produce a signal that usually defines the amplitude of the sound. We want that when pressing a key of the controller, the sound is triggered, and when the key is released, the sound should fade. However, the increase and decrease of the sound should be somewhat natural. In the diagram, we can see a very simple circuit, which is basically an RC circuit. This receives a signal called gate, which comes from the keyboard. When a key is pressed, the signal is 5 volts, and when the key is released, the signal goes back to 0. If we feed this signal into the RC circuit, we can get the results shown in the simulation. The voltage of the output increases softly, and when the key is released, the voltage decreases. The time it takes to increase is usually called attack time. The time it takes to decrease is called release time. If we want to change the attack and release times, we can replace the resistor by a potentiometer. However, this envelope has a disadvantage. The attack and decay cannot be controlled independently. If we want to have different values, we need a way of detecting when the envelope is increasing and when it is decreasing. One way of achieving independent attack and release times is to use diodes to create two paths. If you remember, when we mentioned diodes, we describe them as a device that allows the current flow on a single direction. In this case, when the gate is 5 volts and the voltage is increasing, the diode D2 will block the current, while the diode D1 allows the flow through the resistor R1. The value of the resistor R1 is 1 kilo ohm, therefore it will charge the capacitor faster. When the gate is 0 volts, the capacitor will find a discharge path through the resistor R2 and diode D2. The diode D1 will block the current. In this case, the resistor R2 is 56 kilo ohms and the discharge will be slower. In the simulation we can see the results. You can see that the envelope rapidly increases, and when the key is released, the signal has a more natural decay. If we replace the two resistors by potentiometers, we can control independently the attack and release times. Now we have all the blocks necessary to make a synthesizer. In this diagram, I have connected them together and run a simulation of the whole synth. Let's explore a little bit the simulation model directly in System Modeler. This is the actual simulation model. The nodes are produced by this sequencer, which generates control voltage for the two oscillators and also the gate signals. We can open the oscillator block to see the components. Here we can see the different parts of the oscillator. We have the input voltage control, and it goes into the exponential converter, which is built with these components. Here we have the core of the oscillator, which is the variable integrator and the comparator. Then it goes into the circuit that converts the triangle and the square into a saw wave. Here we have the pulse width generator, and then we have 3 potentiometers to control the levels of each waveform, and all of them are mixed by this simple mixer. The two oscillators are connected to the filter. This is the diagram of the filter that we saw before. The low-pass output of the filter goes into the VCAs. These are two copies of the same circuit, and these are the circuits that we showed before. The gates coming from the sequencer go into the envelope generators, and as you can see, there are two copies, and each envelope generator is controlled by these two potentiometers. We have as well an LFO, which is connected to the VCF in order to modulate the cutoff. And that's basically the whole synthesizer structure. This is how it sounds. When I was preparing this course, I built all the modules using breadboard PCBs. The process consists on placing the components and solder them using wires. It is a very time-consuming labor, but very rewarding. The panels of the modules are 3D printed using two colors. Here you can see all the modules: the oscillators, the filters, the VCAs, the envelopes, and the LFO. And I also built a simple mixer. Let's listen to a small demo I recorded using this system, that way you can have an idea on how this synthesizer sounds. As I mentioned in the beginning of the lesson, the circuits work fine, but a few things can be improved. For example, for the oscillator, I did not put much effort on adding temperature compensation. The voltage to exponential current converter needs to be carefully built using transistors with similar characteristics. In the literature, we can find how to do this improvement. It is important to select the best component for the job. In my case, I built all the modules using the parts I had in my parts box. I used the TL074 and 72 op-amps everywhere. These op-amps are good, but for example, in the comparators, we could use specialized integrated circuits. In these modules, I use as reference the power supply voltage. My power supply is very good and it provides a stable plus-minus 12 volts, but it will be better to use voltage reference to generate the constant voltage needed. Some modules, like the oscillator, do need calibration potentiometers, for example, to tune correctly the oscillator. In all the other modules, I did not add calibration potentiometers. They behave fine, but if you build more modules and want them to behave consistently, the calibration potentiometers will help us tweak the modules to match better. Decoupling capacitors are a must for all circuits. They help the power distribution by having a small reserve of energy close to every IC. In my modules, I did not add many of them, and I found that some of the circuits do need it, like the comparator. In general, it is good to add them. I would like to close this course giving you a few recommendations on what to read if you want to learn more. Here is a long list of the books and resources that I use when creating this course. If you want to know why I pick each book, you can read the notes of this lesson where I cover in more detail each book. A few highlights are Introduction to Electric Circuits, which was the main book I used as reference for this course. Practical Electronics for Inventors is a book that I highly recommend for beginners. And if you want to learn more about synthesizer circuits, probably the best resource is Professor Aaron Lanterman's YouTube channel, which has a long playlist dedicated to the topic. My other pick will be Make Analog Synthesizers, which has a lot of practical information and builds a small and fun synthesizer. If you want to find more about the things I make, here are some links. First, you can find the blog post that I have published on the Wolfram blog. In this post, I show how I use Wolfram tools to model and simulate synthesizer circuits. Then you have my website, volt-dsp.com, where I have a blog with some interesting topics, and you can find there the software and hardware I make. Last, there is my YouTube channel. I have not uploaded many things recently, but I have some tutorials on how to model circuits and make them audio plugins.